Hello to everyone, I am Manuel Vincitorio, student in Master Degree Program in Advanced Automotive Engineering at UniMore University. In this video, I'm going to explain the project regarding pipe-induced vibration that me and my teammates have made within the course of Mechanical Vibrations, headed by Professors Francesco Pellicano and Antonio Zippo. First of all, a little overview about what we are going to see during this presentation. We will go through our team composition, the problem definition, the theory and the formulation, the numerical implementation with the use of Matlab software, the results, the conclusion, and the references used. This is our team composition. I am the chairman and the speaker of the group, and then all my colleagues. Milano Gabriele and Micucci Francesco works as a technical developers. Mattetti Lorenzo is our graphics, Basil Senni is our coordinator, Moroni Filippo is our researcher, and then Messina Simone and Montanari Luca works as a numerical developers for Matlab software. The aim of this project is to study possible vibration problems related to the effect of a fluid flowing inside a pipe. The objective is that of create a model, find the natural frequency for different fluid velocity, the critical speed, the mode shapes, and the transient response, due to a point force applied at the midspan of a simply supported pipe. We will take into account only transverse vibration of the pipe due to a constant fluid velocity U. We wanted to find a system which had a similar characteristics of our model, since we have considered a pipe with a length of 5 meters made of steel, and we have found a similarity in an outboard marine engine fuel injection system, which take the fluid through the injectors. The combustible fluid needs a system of pipes, filters to remove dirty, to protect pipes and mechanical components from clogging or damaging. Two types of pumps are present, the low-pressure pump, which brings the fuel to the high-pressure pump, which in turn pushes it up to the injector. This system is highly subjected to the production of vibration because of the kinetic energy released from the engine. So, it's necessary to dissipate it by anti-vibration mounts, called silent block. It's important to say that the vibration level, if unchecked, can adversely affect the lifespan of a piping system, and it can consequently affect the operational capacity and lifespan of the plant which is part of. The usual initial response to check vibration is slowing down the system and checking the support, but this results in reducing system capacity. Other methods include making flow rate lower than the defined critical speed or varying the elasticity of the supports. The pipe system is modeled with the following assumption. The pipe has been assumed as a Euler's beam excited by the inertial force Fi, due to the motion of the fluid inside, characterized by the velocity U, considered constant. Only transversal displacement W of a pipe section has been considered, omitting axial displacement U. Small amplitude of vibration, so a linear analysis it carry on. Starting from this assumption, the equation of motion can be written as follows, where inertial force is calculated considering only the component of the acceleration in z direction. The equation of motion assumes this form, where capital M represents the mass of the fluid per unit length. Then, considering the following substitution and physical quantities, the equation of motion can be transformed into a non-dimensional form, introducing also terms related to the axial load like pressure P and preload T0, and to the internal damping of the material. So, starting from the non-dimensional equation of motion, the Galilean projection is made the derived equation using this substitution. The trigonometric eigenfunctions are considered on a unitary length due to the non-dimensional nature of the equation. Now, the equation of motion can be transformed into a linear uncoupled multi-degrees of freedom system, in our case, 5 degrees of freedom. Hence, the equation of motion can be written in the matrix forms in this way, where A is the matrix which describes the system and from which is possible to evaluate the natural frequencies and the modes. We know that the system is excited by a point force located in the midspan, and it's defined by multiplied F1 of t, which represents the time behavior of the forcing, considered as a half sine square wave, by the Dirac delta function, which identifies the point of the application of the force. The force F is then adimensionalized in that way. The projection of the forcing on the functional space gives the components of the forcing for the Gagliarchy method. The components are obtained through a property of the Dirac delta as follows, where phi of n represents the 5 eigenfunctions, so at the end we can assemble the entire vector G in that way. This is a representation of the system. The next slides will be referred to the numerical implementation of the model in Matlab. So initially, we define the parameters of the system. As I said before, we have considered 5 degrees of freedom, which, in our opinion, are enough to describe the system, and the results also confirm that. The pipe is made of steel and measures 5 meters. We considered an internal diameter of the pipe as 10 millimeters and the external one as 11 millimeters, so a very thin and long tube in order to have an higher excitation of the pipe. Then, we define the metric C, K, and A as calculated in the theory part, and plot the 5 natural frequencies of the system considering U changing. So with a fluid velocity no more constant but variables and ranging from these two adimensionalized values from 0.1 to 15. With the function ag of A, we calculated the eigenvectors and the eigenvalues from which the frequencies are calculated and plotted over the adimensionalized velocity. At this point, in order to obtain all the mode for a constant value of speed, all the values depending on that, so metric C, K, and A, are requantified with a constant values of speed. These are then plotted over beam dimension in the real and imaginary part in the same graph. To compute the transit response, the forcing acting on the beam is defined, and then, using the function myOD, is defined the function to integrate with all the parameters for the integration made by the Matlab function OD45. At this point, all the modes are plotted, one for each graph in time domain to have a clear understanding of the force system behavior. To calculate the transversal beam oscillation when a transit force is applied in the midspan, the W, which represents the oscillation direction, is computed in a cycle, and then it is plotted in a static chart and also in an animated one that depicts the transit behavior over the time. The code for these two charts are present in the following two slides. This is the part related to the plot of the static chart of the transit behavior over the time. And then we have the plot of the animated transit response. At the end, we have the part regarding the definition of the function myOD to integrate in the OD45 function of Matlab. So, our results. The natural frequencies are plotted over the fluid velocity, as is possible to see on the bottom left. And the critical velocity is found to be 3.1, which gives an equivalent fluid speed of 15.7 meters per second. The results was also verified by the use of this empirical equation found in one of our references. As I said before, critical velocity is of great importance in flow-induced vibration and is defined as the velocity at which the natural frequencies is zero, so this point here. Beyond the critical velocity, instability takes over and the pipe vibrates critically. So, one method to reduce vibration in those systems is to have a flow rate lower than the critical speed, which in our case is equal to 15.7 meters per second. We represent the mode shapes of the pipe due to the application of the force, both in time and space. From these 5 graphs, we can see that the first mode has the highest amplitude as we expected. And all 5 modes have a sinusoidal shapes, specifically a sine behavior, due to the fact that we suppose a simply supported beam. It's possible to see in a clearly way that for the second and the fourth mode, the midspan represent a node. The small amplitude of the fourth and the fifth modes can confirm that our approximation to 5 modes of vibration of the pipe is enough to describe its behavior. And finally, analyzing the response of the system due to the sinusoidal forcing function centered in the midspan, we can state that the presence of the single force mode is justified by the fact that we are exciting the pipe in the node of the second mode, On the left, it's possible to see the transient response of the pipe in a static way, and then, on the right, the same response in a dynamic one. So the conclusion. Along this project, we have understood the problems related to the pipe flow-induced vibrations. We have found and computed the first critical speed of the fluid. This characteristic velocity can also be found for the other natural frequency. We have plotted the behavior of the mode in the time and for the wall length of the pipe, and so that the first mode has the highest amplitude with respect to the order 4 modes. All modes have a sinusoidal shapes due to the fact that we suppose a simply supported beam. We also confirm that 5 degrees of freedom are enough to describe the system, due to the small amplitude of the 4th and the 5th modes, and that the presence of the single force mode in the response of the system is justified by the fact that we are exciting the pipe in the node of the second mode. This is the references which we have used in order to complete our project, and thank you for your attention.